Hello students, this is the second video for March 25th, and these problems are intended to be like the classwork number 4, where we're solving logarithmic equations. I'm going to do 3 examples of these. For our first example, we have log of 3x plus 5 equals 2. In the last set of examples, we had exponentials and we changed them into logs. So for these, we're going to change them into exponents. Remember that if there's no base written, it's implied that the base is 10. So rewriting this in exponential form, I have 10 to the second power is equal to 3x plus 5. Or 100 is 3x plus 5. Subtracting 5 from each side, I'll have 95 is equal to 3x, and 95 over 3 is equal to x. Now, what's really important for any log equations is that we have to check our answers, because sometimes if we end up getting an answer that will be illegal, specifically taking the log of a negative number, because there aren't any negative numbers in the domain, we know that the y-axis acts as an asymptote. So we have to make sure that that's not a possibility. So we are going to check our answers. So I'm going to plug in the 95 over 3 here. And I have 95 plus 5. Oops. Because the 3's will cancel each other, right? And so is log of 100 equal to 2? Well, that's really saying, yeah, 10 raised to the second power equals 100. So yeah, that's correct. So the answer that we got is valid. For our second example, come on screen. There we go. Let's look at a different base. Log base 9 of x minus 5 plus log base 9 of x plus 3 equals 1. To use the same process we did on the problem before, we want to combine these two logs together into a single log so we can change to an exponential form. The product rule says that when we have two logs are added together, we could change the arguments to be multiplied. So I'll rewrite this as log base 9 of x minus 5 multiplied by x plus 3. If I multiply that out, I have x squared minus 2x minus 15 equals 1. All right. Now we'll change to exponential form. 9 to the first power equals x squared minus 2x minus 15. I'll subtract 9 from both sides. Because this is a quadratic, I want to have 0 on one side and everything else on the other. And this factors nicely into x minus 6 and x plus 4. So I have two possible solutions, either x equals 6 or x equals negative 4. Now, we don't necessarily reject the negative 4 just because it's negative. We have to check with the original problem to see if it works. And even if it's a negative number and it works within the logs, then we keep it as a solution. So I'll rewrite what our original was. We're going to check. Let's check x equals 6 first. And our original equation was log base 9 of x minus 5 and log base 9 of x plus 3. So when I plug 6 in here, 6 minus 5 will give me 1. And then 6 plus 3 will give me 9. We want to know if this is true. Using the product rule again, you could plug this into your calculator, but using the product rule again, we can multiply the 1 and the 9 together. And so we have log of 9 of 9, long base 9 of 9. Yeah, this is true. This is saying 9 to the first power equals 9. That's true. So x equals 6 is a good solution. Let's check for, I'll do a different color. Let's check x equals negative 4. I can see right at the very beginning that when I put negative 4 in here, this whole thing is going to be negative 9. And I'm not allowed to take the log of a negative number. Same thing here. If I put negative 4 in here, I'm going to end up getting a negative 1. And so for both of these, we won't be able to take the log. So x equals negative 4 is not a solution. In this case, we only have one solution, x equals 6. All right, for our third example, I'm going to do something similar to what I just did, but instead of having plus in the middle, I'm going to have a minus in the middle. We know that using the quotient rule, the minus sign means that the two arguments here are going to be divided. So to combine this into a single log, I'll have the x plus 1 as the numerator and the x minus 1 as the denominator. Once I've got it in a single log, I can change it to exponential form. So 5 to the second power equals x plus 1 over x minus 1, or 25 is x plus 1 over x minus 1. Now, whenever we have an equation that has denominators like that, we want to clear the denominators. So I'll multiply both sides by that denominator so that I can clear it. So these two are going to cross out, and I'll have 25x minus 25 equals x plus 1. I'm going to put all the like terms together. I'll move the x over to this side, and I'll move the negative 25 over to this side. So we'll have 24x equals 26, or x equals 26 over 24, or simplifying that, 13 over 12. All right, just like before, we need to check our answer to make sure that it's correct. So I'll rewrite our problem. Let's check x equals 13 over 12, and our original was log base 5 of x plus 1 and log base 5 of x minus 1. We want to know if that equals 2. So log base 5, 13 over 12 plus 1, 13 over 12 minus 1. This 1 here is the same as 12 over 12, so I think this would end up being 25 over 12. And then this would also be 12 over 12, so 13 minus 12 will be 1. This will be log of 1 over 12. Yeah, we could check this in a calculator, but I'm showing you how to do this the long way by hand because some of your calculus teachers will want you to know the rules of logarithms and how to do this problem by hand. To check this with subtraction, I know that these arguments are going to be divided. So I'll write this as 25 over 12 divided by 1 over 12. Or, oops, 25 over 12 times 12 over 1. So these 12s will cancel each other. And I'll have log base 5 of 25 equals 2. This checks out. 5 squared is equal to 25. So correct. So scrolling back up, our original answer here, x equals 13 over 12, is correct.